How do you compute the XOR of all integers from 1 to n? To do that, recall an important property of XOR, that is 0 XOR x is equal to x. Therefore, this problem is same as computing the XOR of all integers starting from 0 instead of starting from 1. Then let's create a matrix where the ith row of the matrix would contain the binary representation of integer I, and this matrix is 0 indexed. In this matrix, for any bit position I, you can notice that it follows a pattern of 2 to the power I zeros, followed by 2 to the power I ones, followed by 2 to the power I zeros, followed by 2 to the power I ones. Then let us create bounding boxes of height 4 in each column of this matrix. So you create bounding boxes of height 4 here and for each of these columns. Then in these boxes you can notice that they will either contain all zeros, or they will contain all ones, or they will contain identical number of zeros and ones. Why is the last statement true? It follows from the repeating pattern of binary numbers, that is it will have 2 to the power I zeros followed by 2 to the power I ones, and this is true in general as well, not just for this problem. Therefore, you can claim that each box will have XOR equal to 0 because it has identical number of zeros and ones, or the ones cancel out amongst themselves. Now, using just this piece of information, let us see how we can solve this problem in constant time. First of all, assume that when you added these boxes, no element was left behind and no element was outside the box. So if all the elements fit inside the box and the XOR of each of the box is 0 and 0 XOR 0 is also equal to 0, then you can claim that if the matrix has the number of rows that is divisible by 4, then the answer will always be 0. But remember that we padded a 0 at the start. Therefore, the last element of the matrix won't be 8, it will actually be 7. Therefore, if n modulo 4 is equal to 3, then the answer is always 0. But what happens when just one single element is missing from the box? That is, one single element is outside the box. If one element is outside the box, you can use the property of XOR. That is, if you want to compute the XOR from 1 to n, you can split it into two segments. One is the XOR from 1 to n minus 1 and the XOR with n. But notice that the XOR from 1 to n minus 1 is actually equal to 0, because if you remove this lone element, then all the remaining elements will fit inside the boxes. So 0 XOR n, we already discussed, is equal to n. Therefore, you can claim that if n modulo 4 is equal to 0, then the answer will be equal to n. Then let's discuss what happens when there is one element that is missing, and that is why the last box is not being created. In other words, what happens when 3 elements is outside the box? So saying that 3 elements is outside the box is identical to saying that one element is missing from the box being completed. So you can use another property of XOR, that is, if a XOR x is equal to 0, you can transfer this x to the right hand side. Therefore, if you need to compute the XOR of all of these integers, what happens when you add the missing element? So if you add the missing element, then the last box will be completed and the answer will be 0. So that is why if you add this missing element, the answer will become 0. But you were interested in this quantity, so you can actually send this missing element to the right hand side, and therefore you can claim that if n modulo 4 is equal to 2, then the answer is n plus 1. And lastly, let us discuss what happens when two elements are outside the box. So if two elements are outside the box, and you can use the property that the XOR of the boxes is 0. So that is why the XOR of the previous segment is 0, and we only need to analyze the XOR of n minus 1 with n. But here notice that if two elements are outside the box, then n modulo 4 will be equal to 1. That means that n is an odd number. if n is an odd number, it will contain a set bit at the last index, and n minus 1 will contain 0 in this position, and all the remaining bits will be identical. So if you XOR these two elements together, these bits would become 0 and this last one would remain. So therefore if n modulo 4 is equal to 1, the answer will be 1. So this is the summary, that if all the elements fit within the boxes, the XOR is 0. If one element is missing to complete the box, the answer is the missing element that prevented the box from being completed. If one element is outside the box, the answer is the element that is outside the box. And if two elements are missing, then the answer is the bitwise XOR of the last two elements, which is always equal to 1 if the last element is an odd number. But if I were to ask you to find the XOR of 5 to 35, how would you do that? To do that, you can use an important property of XOR. That is, if you want to compute the XOR in a continuous range, you can compute the XOR from 1 to r, you can compute the XOR from 1 to l minus 1, and then XOR these two values together to get the answer for 5 to 35. So you can compute the answer for 1 to 35, for 1 to 4, and then XOR these values together to get the answer. Now, if you have really understood the concept of boxes that I have taught you in this video, here is an exercise for you. You are given n integers from 1 to n. You need to count how many set bits are there in all of these integers combined at position p, and p can vary from 0 to 30. You will see that if you use the box trick, you will not encounter any off by 1 errors anymore, because otherwise it was very difficult to count the number of set bits. There was a lot of if else and ternary operators that you needed to apply. But if you visualize the box trick, you will be able to come up with a very simple expression for computing the number of set bits. Let me know your answer in the YouTube comments.